Welcome to the Electrical and Electronic Engineering lecture series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is two-port networks and transmission lines, part 1. Any electrical network in which energy is fed in at one pair of terminals and taken out at the second pair of terminals is known as a two-port network. It can be in the form of attenuators, filters, amplifiers, transformers, or in any form of power or communication transmission lines. Two-port networks are said to be passive if they contain only passive circuit elements and active if they contain sources of EMF. However, I will be using a simple passive symmetrical circuit for our study of two-port networks vis-a-vis telecommunication transmission lines. When studying two-port networks, two parameters are very important: the characteristic impedance of the network and the insertion loss. We'll be considering the characteristic impedance and insertion loss much later. The input impedance of any two-port network is the complex ratio of voltage to current at the input terminals. This input impedance normally varies according to the load impedance across the output terminals. For any passive two-port network, a load impedance can be found which will give rise to an input impedance which is the same as the load impedance. For a symmetrical network, there is only one value for this impedance called the characteristic impedance denoted by Z0. For an unsymmetrical network, this is called the iterative impedance, and its value will depend upon which port is taken to be the input and which one as the output. Now, if we consider a typical symmetrical T circuit as shown in Fig 1, terminated in an impedance equal to the characteristic impedance, such that V1 over I1 is equal to V2 over I2 is equal to Z0. It can be seen from the input port that Z0 will be equal to square root of Z1 into Z1 plus 2Z2 if you use any of the circuit theory to solve for Z0. And when the output terminals are short-circuited, the Z short circuits will be given as Z1 into Z1 plus 2Z2 all over Z1 plus Z2. When the output terminals are open-circuited, we have that Z open circuit will be equal to Z1 plus Z2. Therefore, Z short circuit multiplied by Z open circuit will give you Z1 into Z1 plus 2Z2. That is equation 2. If we compare equations 1 and 2, it will yield an important general relation given as Z0 equals square root of Z short circuit times Z open circuit. We call that equation 3. Now, this concept of characteristic impedance is important in telecommunication system since it facilitates the design of networks with specific transmission properties. Characteristic impedance of a communication transmission line. If we consider a length of uniform two-conductor line connected between a source and a load, within any short length, we can determine both the energy storage and energy dissipation in the line. Energy dissipation occurs both in the conductors and in the dielectric, while energy storage is manifested as magnetic and electrostatic energy. A typical circuit displaying the above properties of such a transmission line is shown in Fig 2, where a unit length is considered to have an inductor, resistor, capacitance, and conductance. If the transmission line is of infinite length, all the power fed into it will be absorbed, and as one moves away from the input, the voltage and current will continue to decrease as a result of voltage drops across the inductance L and current leakages through the capacitance C. As one moves away from the input towards the load, the impedance seen at any point in time is also Z0, although the current and the voltage get lowered. Therefore, it does not matter what the circuit to the right consists of, provided it has input impedance equal to the characteristic impedance of the line. The input terminal sees only a piece of line that is followed by a circuit which has the input impedance equal to Z0. Therefore, at any point in time, we can compute or measure Z0 at the input of a transmission line if the output is terminated in Z0. From our knowledge of filters, the characteristic impedance of an iterative circuit consisting of series and shunt elements, as shown in Fig. 2, is given by Z0 equals square root of Z over Y, where Z is equal to the series impedance per section, given as R plus J omega L, and Y equals the shunt admittance per section, given as G plus J omega C. Therefore, from equation 4, Z0 will be square root of R plus J omega L over G plus J omega C, called equation 5. From equation 5, it can be seen that the characteristic impedance of a transmission line is a complex equation, more especially at radio frequencies. Here, the resistive components of the equivalent circuit become insignificant, and the expression for Z0 reduces to Z0 equals to square root of J omega L over J omega C, which is equal to L square root of L over C. Equation 6 shows that the characteristic impedance is resistive at radio frequencies. Now that leads us to losses in transmission lines. Energy impressed at the sending end of a transmission line can be dissipated through radiation, conductor heating, and dielectric heating. Radiation losses arise because a transmission line may act as antenna if the separation of the conductors is an appreciable fraction of the wavelength. Radiation losses are difficult to compute, but it is known that they increase with frequency for any given transmission line, eventually making the line unuseful at some high frequencies. Conductor heating, known as I square R loss, is proportional to current and therefore inversely proportional to the characteristic impedance. It also increases with frequency. Electric heating is proportional to the voltage across the dielectric and hence inversely proportional to the characteristic impedance for any power transmitted. It increases with frequency because of gradually worsening properties associated with increasing frequency for any given dielectric medium. For air, dielectric heating is negligible. It is important to note that the velocity of light and all other electromagnetic waves depend on the medium through which they travel. Thank you for listening to this part 1. Subscribe, like, and follow so that you get to part 2 of this topic, two-ports and transmission lines, for the conclusion of the topic. Thank you for listening.